Okay, class, welcome back. And today we're going to continue with chapter 3, and we're going to do section 2, which is synthetic division. And so in this case here, we're going to talk about how to do synthetic division. We're going to introduce the remainder theorem and then talk about potential zeros of polynomial functions. And so this is the division algorithm. The division algorithm is how we divide polynomials. So you've seen this before. This is how what we used in order to divide polynomials using long division, right? And we saw this in the review, okay? So for any polynomial f of x, we can find a g of x that we can divide by, and there exists some quotient q of x and another polynomial r of x, a remainder function, such that we can rewrite f of x as a product of these two functions with a remainder, okay, where the remainder is either 0 or some degree less than g. So this degree has to be less than this degree, and this degree has to be less than this degree, and of course this has to be at least 1 or more. Now synthetic division gives us an efficient way of finding a quotient and a remainder where x minus k is the divisor. Okay, so we're looking at dividing by a binomial. So this is specific. This pertains only when we're dividing by some binomial x minus k, where k is a constant. Okay, so now in long division, this is the process we go through, right? And we basically go until we reach the end here, and whatever we end up where here is our remainder. This is our r of x. Okay, this is our g of x. This is our f of x, right? Our dividend. This is our divisor, and then of course this is our quotient, our q of x. Okay, and so this is the way we would do it long division. Now with synthetic division, though, we start by, to develop the synthetic algorithm, or the synthetic method of doing this, let's start with just getting rid of the variables and see how this looks. Okay, so let's do the same thing. We're going to omit all the variables, keep the coefficients, and see how this looks. Okay, so again, we need to get rid of the 3, so we put a 3 here, bring the 3 up, and then we multiply. We get the minus 12, and then we subtract, and then we get 10, and we need a 10 here, so we put a 10 here, so we're repeating this. Then negative 4 times 10 gives us minus 40, and then we subtract, and we drop down, and then we get 40. So 40 has to go up here, and we need a 40 here to get rid of, again, because we're subtracting. Negative 4 times 40 equals minus 160, and then we get our remainder. So we get the same result. These are the coefficients of the quotient, and this is the remainder. Now, let's get rid of the ones that we're writing down below, and let's just bring it up. So now this time all we're doing is bringing the 3 up and then multiplying by negative 4, and that gives us a negative 12. Subtract, bring it up, negative 4 times 10 is 40. We put the 40 here, subtract, and then bring down, and we get negative 4 times 40 equals negative 160. So we're using this one to get this one. Then we multiply here, this times this to get this one, and then this times this to get this one, and then finally we end up with our 10, our remainder. Okay, so again, we get the same result. Okay, so now in this case here, why don't we do this? Instead of writing it all up here, let's write it down here. Okay, so what we can do is we can start by dropping the 3 down. Then we take negative 4 times 3, that gives us negative 4. Subtract down, we get 10. Negative 4 times 10 is negative 40. So we subtract down, that gives us a positive 40. Negative 4 times 40 is negative 160, which we put here, and we get 10. And we're done, because as soon as you get to the end, this is your remainder, and the first 3 are the coefficients that we got before. Now, to make this simpler, we're going to use the additive inverse of this. And so we're going to use, instead of minus 4, let's use positive 4, and instead of subtracting, then let's add. So we do the same thing. We drop down, multiply, put the product here, add down, multiply, put the product here, add down, and then multiply, put the product here, and add down. And then we get the same thing. So we get the exact same answer, but it simplifies things a little bit because then all we have to do is multiply and add. Multiply and add. We don't have to worry about the subtraction. And so that is how we do the division algorithm. And so what we get is when we're done, these are the coefficients for the quotient, and then this is the remainder. And so the remainder is 10, and we divide by x minus 4 because it's the remainder. And so the quotient, the function that we started with, can be rewritten as this plus the remainder. Okay, so this is the quotient plus the remainder. Okay, that's this. Well, this is the quotient, right? The whole thing. The quotient plus the remainder is the answer. That's what we get when we divide. Okay. Now, avoid errors. Use 0 as a coefficient whenever there's missing terms. So we always want to include missing terms when we're setting up the division, else you'll make a mistake. So in this case here, there are no missing terms, right? They all go in decreasing order. So now we're going to use synthetic division. So here, remember, the form has to be x minus k. So what is k in this case? It's going to be minus a negative 2, so k is negative 2 in this case. Okay, so we got to be careful when it comes to that. Now, so there's our negative 2. And so now we're going to set up our division. So here's our k. Here are the coefficients. And now what we're going to do is we're going to drop the 5 down and then start the process. Okay, so we drop the 5 down and then we multiply, right? And so we get negative 10. Then we add down and we multiply. And then we add down and we multiply. Okay, and then we add down. And so we get negative 10. So these are the coefficients for the quotient, and this is the remainder. So we know that when this is divided by this, we get a quotient plus a remainder. Okay. Now, since the divisor x minus k has a degree 1, the degree of the quotient will always be written as 1 less than the degree. So now we know what to do with these. So if we have we're going to know the degree of the original polynomial that we're dividing. Okay, so all we know that these are going to be the coefficients of the new resulting polynomial. Okay, the other factor, but it's going to have a degree 1 less. Okay, and so what we're going to do is this started with a third degree, so that means this is going to be 5x squared minus 16x plus 4. And so that's going to be our quotient, and then the remainder is going to be negative 10 divided by x minus 2. So this answer, okay, so this answer here, this, when we divide this, is going to equal this plus the remainder. So the quotient plus the remainder, okay? Now the special case of the division algorithm is for any f of x and any complex number k, there exists a unique polynomial q of x and a number r of x such that the following holds. So this will always hold, that we can rewrite f of x as x times k times q of x plus r of x. Okay, and so all we're really doing is we're taking this here, we're taking this and we're multiplying everything by the divisor. And so we get f of x is equal to g of x times q plus the remainder, negative 10. So this is the remainder divided by the divisor. Okay, now the mathematical statement here is exactly that. Okay, so this is the mathematical statement that illustrates the special case. Okay, so f of x is equal to some value p of x, or excuse me, g of x times q of x plus r of x. Now the remainder theorem then is a result of this. So if the polynomial f of x is divided by some binomial of the form x minus k, then we know that the remainder is equal to f of k. So whatever the remainder turns out to be, it's going to be the same as the value of the function evaluated at k. So that's going to be a good, helpful theorem. So in this example here, we said for this f of x, we divided by x plus 2, and the remainder was negative 10. So that means f of negative 2 is equal to negative 10. That's what the remainder theorem says. Okay, right? So we can easily verify this by plugging in negative 2 for x into f of x. So if we plug in negative 2 and then simplify, we get negative 10. Okay, and again, make sure you use parentheses when necessary. Okay. Now, an alternative way to find the value of the polynomial is to use synthetic division. Okay. So why? Use synthetic division to get the remainder. And once you have the remainder, you have your answer. So like we did before, we're going to use negative 2 as our k value, and then we're going to write down the coefficients, and then we're going to use the algorithm, the synthetic division. So we drop the 5. Negative 2 times 5 gives us negative 10. We add down, get negative 16. Negative 2 times negative 16 is a positive 32. We add down to get 4. And then negative 2 times 4 is negative 8. And then we add down to get negative 10. And of course, we get the same answer. So we know that this is equal to f of negative 2. Now, what about this one? We want to use the remainder theorem to find f of negative 3. Well, this is going to be our k value, so we're going to use synthetic division to divide this by negative 3. And so if we start with negative 3 and we do the coefficients, right, notice that we missed a term here, 3, so we put a 0 here, okay? Make sure you put the 0, okay? It will prevent you from making unnecessary mistakes. Okay, so we drop down the negative 1. So negative 3 times negative 1 is positive 3. Drop down or add down 3. Negative 3 times 3 is negative 9. We add down, we get negative 6. Negative 3 and negative 6 make 18, positive 18. We add down, we get 14. Negative 3 times 14 gives us a negative 42, and if we add down, we get negative 47. So we know that f of negative 3 in this case is equal to negative 47. And you can verify that by plugging in negative 3 into f of x. Okay, now, testing for potential zeros. Okay, now what is a zero? A zero is when the polynomial function is 0. Okay, so whatever k value that makes the function 0, that's going to be a 0. So the 0 of a polynomial is any number k such that f of k equals 0. So the real number, now again, we're talking about real numbers. The real number zeros are the x-intercepts of the graph. So you could have non-real zeros. But if it's a real 0, then it's where the graph intersects the x-axis. So it's an x-intercept. Okay, so you can find the zeros when you find the x-intercepts. Okay, now those are going to be the real zeros. Now, the remainder theorem gives a quick way to decide if a number k is a 0 of the polynomial function defined by f of x as follows. 1, use synthetic division to find f of k. Okay, simple enough. We've been doing that. 2, if the remainder is 0, then f of k is equal to 0, and hence k is a 0 of the polynomial f of x. If the remainder is not 0, then k is not a zero of the function f of x. Okay, so a zero of f of x is also called a root or solution of the equation f of x equal to 0. Okay. Now, decide whether the given number k is a zero of f of x. Well, very simple. We're going to use synthetic division, and we're going to divide by positive 1, and we're going to use the coefficients here, and we're going to just see if the remainder is 0 or not. That's really the deciding factor. So we set up our terms, and now we go through the process, and we go drop the 1, and we multiply, right? And we get 1. So, and 4 plus 1 is negative 3. And then we multiply, and we get 9 plus a negative 3 equals 6. And then we get negative 6 plus 6 equals 0. And now, since we got the remainder 0, this means that 1 is a 0 of the polynomial. It's an x-intercept, in other words. And so we know that the x-intercept in this case is going to fall on 1, 0. Okay? Now, what about this one? So here we're going to use negative 1. And so all we're going to do is do the same thing. We're going to see if the remainder is 0. So here's negative 1, right? So that's your k value, negative 1. We're going to do the same thing. We drop the 1 down, multiply, add down, multiply, add down, multiply, add down, and then multiply. Now here the remainder turns out to be 6, which is not equal to 0. So therefore, negative 1 is not a 0 of the polynomial. And negative 1, 6 is not the x-intercept. Okay, so negative 1 is not a 0 of f of x, but it is on the graph, right? Now, what about this one? So now we're going to use a complex number. Well, guess what? We're going to do the exact same thing. Okay, just a little bit more complicated, a little bit more tedious, but you just, as long as you keep everything straight, you'll do fine. And so we're going to use k as 1 minus 2i. So again, here's our coefficients that we got from our polynomial. And now what we're going to do is we're going to drop and then multiply. So here we get multiplied by 1. We get 1 plus 2i. And now we're going to add down. Well, negative 2 plus 1 gives us a minus 1 plus 2i. And now here we're going to do 1 plus 2i times minus 1 plus 2i. And so this is going to be this work right here. So we're going to multiply these two together, and we get minus 1 plus 4i squared. Now remember, this is I squared is what? I squared is negative 1. Okay, so this is going to be negative 1 minus 4, which is minus 5. Okay, and so now we're going to get minus 5 here, and we go through the process again. So we're going to get negative 1, and then this is going to be 1 times negative 1. We're going to get negative 1 minus 2i. Okay, and if we add these, we get 1 minus 2i. And in this case, we're going to get positive 5 when we multiply them together. And of course, we get 0 as a remainder. So this means that this is a complex root of the equation f of x equals 0. Or it is a 0, a complex 0. Okay, so it is a 0. Okay, and that finishes up. Okay, and that finishes up today's lesson and today's section. So again, please make sure you're going through the homework problems. Make sure that you're doing exercises at the end of the chapter, practicing other examples in the textbook, and going through the guided notes. And just make sure that if you get stuck in anything, or you're just not sure how to go on to the next step, or if you're just not sure if you have the correct answer, email me. Or actually, better yet, bring those to class. Always bring your questions and your work to class, because that's where the learning is going to happen. Okay, until then, have a great day.